Hello everybody, Dr. Powers here. We're going to be, I'm going to walk through the lab for this week, which will also highlight some of the functionality that'll be handy for us using Stat Powers. So we're really concerned this week with inference on quantitative data. So that means numerical data and only a single sample. So basically just a short list of numbers that are all coming from one population measuring one variable. Before we do, we want to kind of get a sense of the central limit theorem and how it relates to the normal distribution. And so that's what the first lab is about. So it's actually going to be, we're going to be using the normal probability calculator for this one. You're directed straight to it, and actually from Stat Powers, you can find it under continuous distributions. I'm going to just pull it up right here, the Gaussian normal. And it'll look like this. Now what we want to be doing here is set it up with a mean of 100 and a standard deviation of 20. So you know the normal distribution is parameterized by two numbers, the mean and the standard deviation. The mean tells you where the center is, and the standard deviation tells you how far it spreads. And you can use a rough rule of thumb of 3 standard deviations gets you about 99.7% of the data. So basically 3 standard deviations out gets you almost everything. Okay, so let's continue on. We're going to be doing some sampling, and we're going to look at samples of size 20. So open up the sampling panel, and we're going to set the sample size to 20 and the number of samples to big. It's going to be 1,000. Some large number will do the trick. Now I'm going to sample and generate a whole bunch of data. On the left you can see we've got data from our normal distribution, and each one of these rows a mean is calculated. So what we're going to be looking at is the distribution of the means. So each of these sample means comes from 20 random values coming from a normal distribution. Okay, so let's look at those. We're going to start by looking at the histogram. And okay, the histogram looks like a normal distribution, and that should come as no surprise. But the thing that's different about this is if you see, the spread goes out from like 86 on the left to 115 on the right. If you look back at the population that we sampled it from, right? So this actually, I'll just string it. So this goes from 30 up to 170. And so this distribution is a lot more compact, although it's scaled out because it's scaled out to, well, this is a full data set. We don't see sample means that range as high as 170 or 160. And that's actually a consequence of the standard deviation of sample means. And this is something that you'll see when you look at the statistics. So here I have a mean of 99.9177, very close to 100. And I have a standard deviation of 4.4873. Rather than the population, which, recall, had a standard deviation of 20. And the reason for that is there's a formula that controls the standard deviation of the sample mean, and that is you take a population standard deviation and you divide by the square root of sample size. Now the square root of 20 is about 4.5 or so. So what is 20 divided by 4.5? Yeah, I mean, it comes out to be about 4.5. In fact, this is going to be 20 divided by square root 20, which is square root 20. So 4.48 seems like actually what we would expect to see. Okay, now let's see. Is there evidence? I know we looked at the histogram, and we can look at the normality plot. The QQ plot is very strong evidence that these sample means are distributed along like by a normal distribution. That's very clear from this QQ plot. The worm plot I've mentioned before it takes away the diagonal trend and allows you to really see if there's any sort of deviation. And it wiggles. It always wiggles a little bit, and it exits this kind of tolerance band a little bit, but this is 95% tolerance band. So, and definitely 95% of the points are within it. So there's really no cause for thinking that the data is not normally distributed. So, okay, what we're going to do next is look at sampling from a non-uniform or non-normal distribution. And so we're going to pull up a uniform distribution, and we can set the lower bound and upper bound to be whatever we like, as long as the lower bound is lower than the upper bound. At the moment, I have to set the upper bound higher first. So let's go to from 100 at the high end and maybe 75 at the low end. And we're going to just go ahead and do some sampling. Let's look at the properties of the population. The mean is 87.5. That's halfway between the minimum and the maximum. Standard deviation of 7.2169. That'll be important to keep in to think about. Okay, so let's do some sampling. I'm going to we're going to start with a sample size of 1, and we're going to do a lot of these samples. So this is actually, you'll see every value I have on the left is exactly the same as the value on the right. The mean of one number is just that one number. Okay, so if I analyze those, this is really just looking at a sampling of 1,000 values from the uniform distribution. They've been sorted from lowest to highest. And if I look at the histogram, it should look like a uniform distribution. It's pretty much uniform frequency from left to right. That's what we expect to see. Normality plot, this is what a QQ plot looks like for a uniformly distributed data. I mean, it's not a normal distribution. So you have the curve down on the right means that the right tail is a lot shorter than we expect on a normal distribution. On the left tail is a lot shorter than we expect. So this is a uniform distribution in a QQ plot. No surprise there. Okay, looking at the sample statistics, you should see the mean 87.1835, which is not very far off from the mean of this population, 87.5. Similarly, the standard deviation of my sample, 7.418, not that far off from the population standard deviation of 7.2169. Alrighty, very good. So, now where are we going with this? So we're going to do the same kind of thing, but just change our sample size to 2 and then resample. And now these means were calculated as the average of 2 values. And we'll see, just with taking 2 numbers from a uniform distribution, averaging them and looking at the distribution of those averages, we'll see a very different shape in our sample histogram. It already has a very triangular kind of shape. So now it's unimodal instead of rectangular. And we'll see in the normality plot, okay, that kind of non-normality tails is still evident, but if you compare it to what we saw before, it's not nearly as extreme as it was before, right? You can see that the curve was a lot more extreme. So what we are seeing is that your sampling distribution is of the sample means, it's becoming more and more like a normal distribution as you increase the sample size and average more values together. We'll also look at the summary statistics, and you'll observe that the mean of these averages is actually still pretty close to the population mean, but the standard deviation is starting to decrease. Remember, it was before it was at 7.4, now it's at 5.04. Okay, you're going to continue that with smaller and larger and larger sample sizes, and observe at what point does the distribution become kind of not really distinguishable from a normal distribution. And that's going to be what the first lab is about. The second one is going to walk you through some inference for a sample coming from some population, a sample of quantitative data. So the scenario here is that 16 samples of steel conduit are buried for 2 years, and then the maximum penetration of the specimens are measured to see how the corrosion has affected it. And so what we want, the alternative hypothesis we're working with is that the mean is greater than 50, because if we have evidence that the mean maximum penetration is more than 50, then that's evidence that we need to that the steel beams are not, the conduits are not acceptable. But as long as there's no evidence that the corrosion exceeds 50, then we're good. So this lab is going to walk you through the steps of the calculation of your test statistic, and actually it's pretty step by step. So I don't really think that I want to walk you through this calculation, but I will just show you how to do the t-test using stat powers directly. So I'm going to actually open up the population over here. The population is a simulated population. Okay, so you've got the variable max pen. So I'm going to take that. We're going to set a sample of size of 16. All right, and then I'm going to click sample. That's all you need to do to get your values. So you're just going to get 16 random values of max penetration. And then we're going to analyze those as a variable. And when you do, the kinds of things you'll be looking at when you're doing a t-test are, first, you should check to see whether or not there's any evidence of non-normality. You look at a QQ plot. There's the QQ plot tends to, there's always going to be some variation from the diagonal, especially with a sample as small as 16. I'm going to look at a worm plot just to see if the variation is within tolerance, and it certainly is. Like, this is tolerable kind of deviation from that diagonal, which means that we really have no reason to think our data is not normally distributed. Or more properly, there's no reason to think that the population from which it was sampled isn't a normally distributed population. We can also check the histogram of our data. And yeah, I mean, with the sample size of 16, this is basically all we can hope to see is just like a mode in the middle, Now, when you're doing a t-test, what you're going to do is pull up the, under hypothesis testing, look for the test for the mean panel. What we're interested in is whether or not 50 is the mean, or if the mean is greater than 50. So I'm going to put 50 in for the null mean, and I'm going to set the alternative to be greater than, because that's the claim that we're looking for evidence to support, that the mean penetration is greater than 50. And when you set those two, your t-statistic is calculated for you, and the p-value is calculated for you. In fact, you can even look at a visualization of your t-statistic. Here it is, kind of out in the tail, further away, and then this in this shaded region is what's called the rejection region. It's a little bit more of a classical approach to t-tests. You can also do a bootstrap t-test, which you're asked about later on in the lab, and that's where basically we rather than assuming normality, we kind of take the population to look just like our sample does. And what we do is we resample many, many times to come up with a simulated distribution of test statistics. And then we see, with this test statistic we observed of 3.9264, we see how extreme that is with relation to those. So I'm going to, this generates the bootstrap t-test, and I can look at my simulated distribution of test statistics. It looks not far off from what my theoretical distribution looked like. And every time you do a bootstrap t-test, you're going to get a different distribution of simulated t-values, and the p-value will change a little bit, but it's not going to change by that much. I'm going to click it a couple times, and you can see that it's every time it's changing a little bit. My p-value is hovering around 0.0028. Okay, 0.0014, 16, 19. Okay, so it's all staying pretty low, and certainly below 0.05. So but in the lab, you're going to actually walk through the calculations and the step-by-step of doing these things, so you understand what's going on below the surface better. Now we want to go through the power calculation. Power calculation can be found under the analysis menu. There's a sample size and power calculator, and I'm going to open it as a pop-up, a new feature added this semester. So looking at a one sample t-test, the bottom panel for the mean sample size power, you can, if in the lab we're looking to see how large of a sample is needed to detect an effect of 2 mils. And so we set the effect size to be 2 and the standard deviation to be our population standard deviation, which if you, I guess our best estimate of that is going to be our sample standard deviation. So let's just go to our sample statistics. Here, mine, I had 5.4566. I'm going to copy that and paste it over. You're going to have different numbers, of course. What this is going to allow you to calculate is, so I want to see what was the power of my test with a sample size of 16. Now, what this is telling me is that for a two-sided test, the power, so this is a two-sided test with a significance level of 0.05. If the true difference was 16, it was 2 with a standard deviation of such, I would have a 26% chance of rejecting the null hypothesis. But actually, we were doing a one-sided test. So in order to handle that, we actually double the significance value, because that 0.05 is split into the two tails with 2.5% in each tail. If we wanted 5% in the right tail, we'd have to put 10 here in order to do that. So actually, our test, our sample size of 16 had a roughly 39% chance of detecting a difference as small as 2 mils, a mean difference. So if the mean was actually 52, we would have had about a 39% chance to reject the null hypothesis. Now, the other part of it's asking, well, what sample size would you need in order to get 80% power? And that is simple to do. You just go click on sample size instead of power and change that power to be our desired power, 49. So this tells us that if we have a sample size of 49, and if the true mean was 52 as opposed to 50, we would have about an 80% chance to correctly identify that the null hypothesis should be rejected. That's power calculation, and you'll read more about it, and it'll make more sense when you work through the lab. I just want to show you how it's done here. The last part is actually fairly similar. It's actually it's a t-test based on data, so you're actually going to be opening up the data set that's called Run 17. The Run 17 is this this in Washington D.C. this 10-mile run, and this is 2017 data. So we're looking to see whether the mean speed runtime has changed from 93.29. There's a couple things that we'll be doing. First off, the time to finish the event is in net seconds. We don't want seconds. We want to have we want to use minutes, and so what we're going to do is create a new variable called time, and define it as net seconds divided by 60. That'll just convert the seconds to minutes, and then we're going to do all our analysis on this. But you're going to, instead of doing the full data set of 19,961 runners, you do a random sample of size 100. You don't need to set the random number seed, but you can. That way you'll have the same sample every time you do the sampling. Anyway, you just have to do that, generate your data, and you can do your t-test from in here. It's all going to, you're going to need to look at the normality to assess whether or not we have, oh, that doesn't look like a very good normal distribution to me. I'm going to look at the worm plot and expect to see this wiggle out of the bounds. Yeah, there's a big weird shape in the lower tail. Let's look at the histogram. Yeah, this is not. There was definitely way too many slow individuals that it's left skewed, and then there's a lot of those outliers. I think we probably see them as outliers in a box plot. No, it's actually just identified as one outlier. So the tail is just really long. So, if you had a small sample size, a QQ plot that looked like that would tell you that you have failed the normality assumption. And so a t-test requires your data come from a normal distribution. However, as we saw earlier on with the sampling from a uniform distribution, even with relatively small sample sizes, your sample mean will tend to be normally distributed even if your population wasn't. So with a sample size of 100, which is what we have here, we can kind of ignore the normality assumption and say we can continue with a t-test, even though we don't have evidence of non-normality in the population. So let's do a t-test. Oh, incidentally, let's just look at if we did a full sample of all 19,000, what would the shape of the distribution look like? Let's look at a histogram. Yeah, you can see you definitely do have it's like you have a normal distribution, but then you have like a subpopulation. And I wonder if there's like two populations that were doing the run, and maybe there was some older people who ended up taking a lot longer. I don't know. But certainly if you look at this, you can see the population is not a normal distribution. It's a bimodal distribution. And that came out in my sample as well. Anyway, let's just talk about the t-test, right? You're going to be putting in 93.29 as your null time to finish in minutes. We're seeing if there's evidence that it's changed. And when I run it with my sample of 100, I do have evidence that it's changed. 0.0173 is my p-value. I have a negative t-statistic, which tells me that my sample mean is lower than this null mean. And you can actually just look at that in your sample stats, summary statistics, 86. So that's faster, right? That's an average. That's a faster speed because it took less time. So oh yeah, I think that's that's basically what you'll be doing with this, and just writing it up and practicing this stuff. So, but in the second part of the lab, you'll actually have the chance to calculate all this stuff by hand. The only thing you can't do by hand is calculate the p-value, which, even if you were doing this, if you didn't have any computer, you'd have to look up p-values using a table or some sort of lookup table thing. And so using a calculator certainly helps make that easier. All right, and I hope this goes well for you, and you get a good sense of what kind of inference we can do on just one sample of quantitative data, but we'll be building on this in the weeks to come. All right, ciao.